So today I'll be doing this physics worksheet. Alright, the first question is: a girl with mass 60 kg slides 3 meters down an inclined plane as shown in the picture. So the degree is 40 degrees. Now the first thing I like to do, as we are asked to find the work done on the girl by gravity, well, let's first make a free body diagram and let's add all the forces. For her weight, force of weight, and then I guess I could draw like the normal force, but we don't really need that right now, so I'll just ignore it. Then we'll split it into horizontal and vertical components. This is the vertical component, and this is the horizontal component, or what we're looking for. The reason we're looking for the horizontal component is because it's going in the direction that the girl's going, which means this isn't really doing any work for her because it's being cancelled out by the normal force. In other words, this ain't doing anything. But then the horizontal gravity, the force, is actually pushing her forward. So that's what we're looking to find. Now that we know what we're looking to find, is how we're going to do it. The degree here, 40 degrees, is the same degree in the triangle over here. Hope it's visible. This is also 40 degrees. Now we can use trigonometry to find the other, this side, which is equal to the horizontal component there. So this is what the triangle looks like. This is 40 degrees. This is x. And this is her weight. Alright, so how we're going to find this now is in our data booklet. There's an equation called where work is force times distance cos theta. This is in our data booklet. But we're going to change it a little. And by this, I'm going to replace the force with the force here is mg. We all know weight is mass into gravity. So we're going to replace it with mg. And the s will stay, but instead of displacement, we're going to use height because it's going down. Well, gravity usually goes down, but there's a horizontal component here. And the cos will turn into a sine. Why? Well, this is because we're trying to find x. This is the hypotenuse, this is opposite, and this is adjacent, which means opposite over adjacent. From SOHCAHTOA, that's sine. So now that we know what our equation is going to be, let's plug our values in. So the girl is 60 into 9.81. This is also in our data booklet. Into 3 into sin 40. This will give us 1,135 joules of work. Alright, so second question is calculate the work done on the girl by the normal force. This will automatically be 0 joules. The reason for that is because this is the normal force of the girl. This is the gravitational force, vertical. They both cancel each other out. So it's not doing any work because she's neither going up nor going down. It's perfectly canceling out. The second reason, the mathematical reason why there's no work being done, is because cos 90 is 0. So anything you multiply this by, no matter what the mass is, no matter what the gravity is, no matter what the height is, it's all going to be 0. This is similar to the second question. A block is pulled with 60 newtons of force, it's 5 kilograms, and it's a 30-degree angle, and it moves 3.25 meters. What's the work done by gravity? There's no work being done, and here's why. This is the force of gravity. Now, this is different to the force that the box is being pulled by, 60 newtons. There's a vertical and a horizontal component. Now, however, gravity isn't doing any work because the box still is moving horizontally while gravity is perpendicular to it. This is the force, this is gravity. Therefore, there's no work being done as it's at a cos 90, 0. The next question asks, calculate the work done on the block by the applied force. How much work is this force 60 newtons doing? The formula from our data booklet is work is Fd cos theta, aka work is force into displacement into cos theta. Well, we're given all of the values here. So the work is 60 into 3.25 into cos 30. This is around 168.9 joules. Alright, the next question is we have to calculate the network of the car. So, what are all the forces? There's tension, which is 8,000 newtons. There's gravity, which is mass into gravity. Then there's the normal force. There's friction, which is in 20. And the gravity component, gravity can be broken into 2 components, vertical and horizontal. And that's the first question. Then the second question. So the network is the sum of the work done by friction, work done by tension, and work done by gravity. Well, horizontal component. The vertical component is perpendicular, and as you know, perpendicular doesn't do any work. So, now the formula from our data booklet is W equals force, where work is force into distance cos theta. Or, if the force's direction is in the same direction of the movement we're looking for, as in the car is going this way, so the friction is going the opposite way, which is why it's going to be negative, but it's still we don't need the cos, the theta, because it's still going in like the incline. So we don't need the cos theta. So this becomes, if we substitute the values, and it looks something like this, where this is work done by friction, force into the distance traveled by the car, as it says is 3 meters, force by tension, distance traveled, this is work done by tension. This mass of the car into gravity, into the distance traveled by the car, sin 30, this is work done by gravity, only counting the horizontal component, which again can be found through trigonometry, as we can see here, through this triangle, where this is 30 as well, and if this is 30, and we know what this is, which is mass into gravity, and then the distance, the formula becomes to find the horizontal component going against tension. Now, if you add them up together, oh yeah, friction made a mistake here. It should be negative here because friction is going the opposite direction, so it should be counted as negative if we take going up or going right as positive. This will give us 6,300 joules. Alright, so 1.4 is saying that there is a frictional force of 4.2, and the rest you can see it's being pulled for 50 newtons is 5 kg and it's at a 30-degree angle. It moves 2.6 meters. Now, what's the speed of the block? There's an important phrase I'd like to highlight, the work energy principle. This principle is that work done is the change in kinetic energy, which is half mv squared initial minus half m final squared. So, in this question, we need to find the speed, right? And they're asking us to find it through the work energy principle. What we're going to do first is find the net work being done on the block. The net work is always a sum of its total work. So, the work done by friction, the work done by the applied force are the two ones here. Now, what they'll be, if you plug in the numbers, is through the formula of Fd cos theta, by the way, it'll be 4.2 into 2.6. This is for friction, and as it is in the direction, as it is like horizontal in the direction of the block that's moving, which is moving this way, then we don't need to use cos theta, but for the applied force, we definitely do need to do that. So it's going to be, oh, not mass, what the hell, it's going to be 50 F D and then cos 30. The reason we're doing cos for the applied force is because the force that we're given is at an angle of 30 degrees, but we don't really care about the vertical component right now. We're only looking at how the horizontal component is affecting the block, because the vertical component isn't moving the box at all. It's not doing any work on the box. It's the horizontal component that's adding work to it. So we're going to use cos theta, as cos is ka, aka adjacent over hypotenuse, so adjacent over hypotenuse. So, and the hypotenuse is the 50, which is why it's going over here. If we add them up together, we will be getting 101.66 joules. Now, how does that help us? Well, this is going to help us find the speed. So, as I said, the work done is actually a change in kinetic energy. And the kinetic energy formula has a velocity in it. So here's what we're going to do. We'll equate the net work done. 101.66 joules. The work is half. Mass is mv squared. We're given the mass, which is 5. And then v squared. Then we'll isolate v. It'll become 5 over 2. Since it's multiplying, we'll divide. So we'll be multiplying by 2 over 5. And then we'll root both sides to get rid of the squared. This will give us a velocity of 6.38 meters per second. The next question asks us that a film star in a car, together 720 kg, drives 4.8 meters down the hill at an inclined plane. there is 23 newtons of frictional force, and the engine itself has 200 newtons of power. The angle is 42 degrees. Question A is asking calculate the work done by the engine. Now work is force into distance. We're not going to use cost because the engine is pushing in the direction of the car's movement. So it's going to be work is force into distance, and then the force is of 200 newtons by the engine, and the distance is 4.8. Therefore, the work is 960 joules. Alright, now B is asking calculate the velocity of the car after moving 4.8 meters. This is very similar to the last question we did this, then ask for this velocity after a certain distance. We'll find the net work done, and then we'll equate it to the kinetic energy formula to find velocity. Now the net work here is done by the engine, by friction, and by the horizontal component of gravity, aka, let me just add that. Nope, that's just gravity, and then this is the vertical component, this is the horizontal component. Alright, so again, let's restate the formula. Sorry, it would be force into distance. This is for the engine. Force into distance. Oops. And then the gravity component, we'll need the sign here because right now it's going like this when you want to find the horizontal component. And then we take this angle is also 42, which means opposite. So we'll take force, which is mass, into gravity, into sine 42, into the distance, which will give us 50,602.2 joules. Now we're going to take this number and equate it to the kinetic energy formula, which is half m v squared. We're given mass already, it's 720. V squared is equal to that. So again, with some algebraic manipulation, such as dividing this by 720 by 2, then dividing and then rooting it, you'll get V is equal to 8.08 meters per second. The next question is a little bit more difficult. State the principle of conservation of mechanical energy. Now, with the conservation of mechanical energy is that KE plus potential, or kinetic energy plus potential energy, they will always equalize. That total mechanical energy, the sum of kinetic and potential energy of a closed system, aka the slide, will always remain constant. So if conservative forces like gravity are acting on the system, aka when the girl is at the top of the slide, she has maximum potential energy and no kinetic energy because she's not moving. And then at the bottom, she has max kinetic energy, aka the fastest she moves is at the bottom, and no potential energy because there's no height. So there's no potential energy to be had. The next question asks, she begins 2 meters above the ground, so the slide's height is 2 meters. And friction is negligible. No friction. Use the principle of conservation of mechanical energy to calculate her speed when she is 50 centimeters above the ground. Find her velocity. Now this question may seem unsolvable at first because we're not given her mass. So how we're actually going to do this is by using the conservation of mechanical energy to equate potential and kinetic energy. So half mv squared is equal to, from the data booklet, mass into gravity into change in height. This is the change in potential energy from the data booklet, and this is kinetic energy, again from the data booklet. What you'll see here is that the masses cancel out. And then we already know what the change in height is, which is 1.5 meters. Now we isolate V, and we know gravity 9.81, also from the data booklet. So V squared equals to 3 into 9.81, because you're dividing by half, so you double it, and then you root it. This will get you 5.42 meters per second. For this question, a bus is traveling up an inclined plane. So, to explain the mark scheme here, I've drawn the free body diagram with all of the forces: the normal force, the gravity, friction, the engine force, and the distance. Now what we're going to do first to find the height difference here is write the net work force equation, which is we add up the work done by the engine, work done by friction, and work done by gravity. Specifically this component, the horizontal component, because it's the ones that's actually pushing the bus down. When it's perpendicular, it's not really doing anything. But we'll realize that the net work is actually the change in kinetic energy. And the kinetic energy formula, half mv squared, has v in it to find the velocity. And we are given the velocity to plug in. So this is the kinetic energy formula simplified, change in kinetic energy of the final minus initial to find the change in velocity. Then this force into distance is the work done by engine, as the data booklet it's giving force is force into distance. mgh is the work done by gravity, and this is the work done by friction. And then we substitute the numbers that we are given in. You'll notice we are missing the h from the work done by gravity to find as x. Then we simplify until we get 3.8 meters. Not per second, just meters. And then the next question is man's pulling up a wooden block up. Now we need to find the force applied by the man. So the free body diagram shows that there are 3 forces acting on it: the applied force, the force by gravity, and the force by friction. So what we're going to do here is, again, we're going to use the net force. Net work done is the change in kinetic energy, which we'll then expand to create the equation where it's F applied into the distance, which is 3 meters. The friction, as the work done by friction, is the coefficient into mg cos theta, into the distance. So then the work done by gravity is mg sine 0. The reason it's sine here is because this arrow is sine, which is equivalent to this arrow, and when we are given this angle, as it's 30 degrees, as it's given here, then this is opposite over our known hypotenuse. So this is why it's sin SOHCAHTOA. The reason why work done by friction is cosine is because that cosine is this arrow, and it's equivalent to the normal force. And from our data booklet, you'll realize that force of friction is equivalent to the normal force into the coefficient. So this is the normal force. This is the frictional coefficient that we are given. Now that that's done, we plug in our values that are known here, applied force, and we'll let this remain be a variable. And then we solve for the change in kinetic energy, which is now that we are given half mass into velocity, the change in velocity, we'll plug that in and we square them. We square the velocities. This will give us 25, and then we can continue on simplifying as they're just constants now, and we will get the force applied is 72.6 newtons. Now the second question will be, what is the power dissipated minute man? We need to read this as power from the data booklet is for force applied into average velocity. So we are given the applied force by part A, and then the average velocity is adding up the final plus initial, dividing it over 2, which will get 2.5, multiply them and we'll get 182 watts of power. So in this question, there's a bullet, 20-gram bullet, it's being lodged into a 7-kilogram box. That means the final mass is going to be 7.020 kg. The frictional force is 10 newtons as we're given. Now we need to find the speed of the bullet and block system immediately after the bullet is lodged. It says to use the work energy theorem. Well, the work energy theorem is that the net work is equal to the change in kinetic energy, and right now the only work being done on the block and bullet system is the force of friction. The force of friction is already given to us, and with the formula of work into being force into distance, we can plug that in as negative because it's going the opposite direction of the velocity we're looking for. It'll be negative 10 into 2. This will be negative 20. So the final speed, how we're going to look at negative 20, and then the change of kinetic energy is given by the kinetic energy formula of half mv squared. So this is going to equal to 0 because it's starting from rest, so there's no kinetic energy. This is what we're looking for. We'll plug in the mass of the final system, which is the mass of. Then after plugging in, we'll get 3.510, and then we'll leave the initial velocity as a variable. You'll realize now that it's just simple algebra, which simplifies into being that the velocity was around 2.39 meters per second. The next question states the principle of conservation of linear momentum in birds, which is that in a linear momentum system, with linear momentum in an isolated system, aka no external forces, that the momentum will remain constant in both magnitude and direction. The next question asks calculate the magnitude of the velocity with which the bullet hits the block, aka what is the speed or u. We'll do that by the conservation of momentum, which is that the mass of the bullet into the initial speed, which is what we're looking for, plus the momentum of the box, which is 0 because it's not moving at all, is equal to the final momentum, aka the mass of the bullet plus the mass of the box. And, yeah. So, just whatever, 7.020 in to the final velocity, which we figured out in A. Again, simple algebra now. That'll be 838 meters per second. Now the next question. Alright, for this question we are given a box 5 kilograms and it is sliding down and we need to find the speed at P. We are given that it is an isolated system, there's no external forces happening. So what we're going to do first is find out the potential energy and the kinetic energy. Realizing that there's no external forces, we can equate the two. After cancelling out the m's and dividing both sides by 1/2, we'll get 2 gravity into height is v squared, velocity squared. We're plugging in our numbers, 2 into gravity given from our data booklet, and 5, the distance between the sides, is going to give us around 9.9 meters per second. The next question we are asked is explain how the kinetic energy at point P is the same as at point Q. The reason for that is because this section is frictionless. So when the block moves from here to here, there's no work being done on the block because there's no friction. Therefore, the kinetic energy is the same. As work is changing kinetic energy, and there wasn't a change in kinetic energy here. The non-conservative force is a type of force that doesn't just depend on how much of it was or what direction it was, it also depends on the path taken, though that definition is a bit vague. In my words, what it means is that it's leaving non-conservative forces leave the system. So, in here, the only reason we were able to solve 5.1 is because we assumed that every force was conservative, that it was all kept in an isolated system, no external forces, nothing leaving the system, nothing coming into the system. But in 5.3, what it actually, non-conservative force is friction, for example. If we had accounted for friction, that means that some of the energy or some of the work done by friction, it doesn't stay in the system, it's dissipated as heat and as sound. So, that's why it's non-conservative, because it's leaving the system. The last question is calculate the slope, the angle of the slope QR, which is this angle right over here. And how we're going to do that is we realize that it's a trigonometry issue, because this is a 90-degree angle, opposite over hypotenuse, aka sine. That means, we'll get the equation sine theta equals to 3 over L, and if we isolate L, we'll get L equals to 3 over sine theta. Now, the next thing you gotta do is use energy principles, aka kinetic energy and potential energy plus or minus the work done by friction is equal to the kinetic energy and potential energy at R. Now, how do we find that? Well, we know that the potential energy is going to be mgh, and we know the kinetic energy from the previous questions as well is going to be the force into the distance. But we can also solve it through the kinetic energy formula from our data booklet is half mv squared, not the whatever I was saying. So we already know the value. We already know the value for that from 5.1 for v. So after we plug it in, we can simplify to get these values, and it's 0 over here at these because at the maximum point there's no kinetic energy, and at the minimum point there's no potential energy. And then the work done by friction is found through L, but that's only the height. We have to multiply this by -3 by -18 because that's force into distance, right? Work is force into distance. This is the distance. Then we multiply it by force to get the work, and the force is given as 18 newtons. So that's -54 over sine theta. And then after that we can simplify for sine theta, and it'll be the inverse of that. So arc sine 27 over 49 will give us 33.36, which is the angle for the slope QR. And that's the entire worksheet. This took me way too long to film. Oh my god.